All right, so we are recording, and I'm going to share my screen here. We're talking about calculus, yay! Or maybe not, you're maybe not excited, that's fine too. As I said, we have to do what we need to do. So calculus is literally about these three words. This is it. This is calculus, rate of change. That is it. You are talking everything calculus in just these three words. Now, I wanted to add today, because I didn't get to mention last time, I really do expect you guys to have some fundamental skills, which I won't be covering. So basic bed mass, order of operations, having algebra skills, knowing what variables are, knowing all your basic arithmetic, including exponents, though I've worked in some little tidbits here and there if you're forgetting some of your exponent rules, but I will not be covering that today. Another thing to keep in mind, this is calculus for machine learners, or I suppose the computer are the machine learners, so the machine learner programmers. So we're not covering all of calculus. We're literally not covering half of calculus. We're only covering derivatives today. And that is a big warning for you guys. When you get to high school or college, you're gonna have to learn a lot more. So this is just the abridged version, and it's already, very complicated. Let's see, I have something in the chat. It's up to you. I will be posting the recordings later, so do with that as you will. I won't preach to you about it. So anyways, that's my spiel. Let's get started. So rate of change. Last time we were talking about this magical variable. It was called M, as I was telling Sierra. Sierra, yeah. I was telling Sierra, M for monte. It's French, slope going up. So I wanted to start off with that exact place today. So I'm gonna scroll on over, and you see I have this graph here. Y is equal to x squared, or alternative, f of x, that's function notation, is equal to x squared. So over here I have the x-axis, over here I have the f of x or y-axis. This is something we saw last time, so hopefully it's familiar to you. And I have a few points labeled on this graph. So I want to start off by analyzing slope or rate of change as we knew it last time. So what's happened last time? Well, last time let's see, I took a line and I just drew it through some points. And I was like, hey, if we have a line like this between 2 points, then what we can do is we can calculate the slope of the line. And I showed you some formulas for this, but the general one is just rise over run. So, how much are you going up or down? That's how much we're going down versus how much we're going left or right. And I'll show you the formula for it again. So rise over run. It's also change in y over change in x. That's what this little triangle means. It's the Greek symbol delta, which means change in. And the way we can write that is, we take the y value of a point number 2, subtract the y value of a point number 1, that's the change in y, and then same thing for the x's. Or I guess in a more convoluted notation, this is the function's output, f of x2, that's the input, minus f of x1, that's the second function's input, that's the second function's output. So in a graphical sense, what we're doing is, let me highlight these 2 points. So let's say this is point number 2, and over here, point number 2. And over here we have point number 1. So what we're going to do is, if we wanted to calculate the slope between these 2 points, we would take, the information from point 2 in orange and subtract the information from points 1 in red. So 0 minus 4, that's what we do for the change in y over here. and 0 minus -2, change in x, you get the slope. It's pretty simple. What calculus does is it extends upon this concept because it adds like a specialized notion. It says, hey, you know what? Like, I don't want to, have these 2 points and then go about all that fancy business of creating a line. What if I just, instead of having like this big long line between these 2 points, what if I pretended that I have a line that is almost basically just touching 1 point? So such a line, let me try and draw it the best I can, is like it barely just goes by the graph, touches this 1 point, and keeps going straight on. So like this, ends off in this direction, ends off in this direction. So notice the difference. Before, we had this line that was going from 1 point to the other. And this line, this blue line in contrast, is just touching 1 point. This is the difference between a secant and a tangent. A secant is like just a fancy word that says this line touches 2 points. A tangent is just a fancy word that says this line just touches 1 point, 2, -4. Does that sound good so far? So here's what calculus says. It says, okay, never mind all that like 2-point business. That's just way too much information. I don't even have time to go look at this other point. Okay, I just want to look at this 1 point and be done with it. So what calculus tries to do is it tries to find a slope for this tangent line, this line that only touches 1 point on the graph. And if you look at our formulas, that's not covered here at all. Like, what's going on here? Like, we have these 2 points in all these formulas, and calculus is out here like, oh, you just need 1 point. How are we going to do that? Well, we're going to have to change our thinking a little bit. We're going to have to change our rules. So let's try this. Instead of saying, I'm going to draw this line that touches just this 1 point, what if I basically did an approximation of that? What if I said, okay, instead of just this 1 point, what I'll do is I'll just move that point over here. I'll just move it ever so slightly to this new point right here. Okay, just a tiny nudge in this 1 point. And what if I then drew a line that goes through both of these points? Now you can see, even with my bad drawing skills, this line is pretty similar to the tangent we had before. The reason is that, if you have just this 1 point touching, or if you have like this 1 point and right next to it another point touching, they're pretty similar, these 2 lines. And we can say that, the slope of this new line that is still touching 2 points, though they're very close to each other, that is approximately equal to a tangent at just this 1 point. Technical wording, the slope of the tangent is about equal to the secant if the 2 points are just really, really close to each other. Now I'll show this, okay? So let's label this second point here. What we want is the second point is almost equal to this first point, right? So we'll say like, okay, this is -1.999 instead of -2. And the second value, oh, I have big numbers here. Maybe it's 3.996. How did I get that? Remember what we do? We always take the x value and plug it in to the function. And if we set x is equal to -1.999, square it, you will get 3.996. So that's what we're doing here. We're taking this first point and getting a second point that is roughly equal to the first point. Everyone following? Any questions so far? So let's calculate the slope again. So last time we calculated a slope that was, this point and this point. That's what we had the first time around. Here's what we're going to do. We're going to calculate the slope of just these 2 points very close to each other. So again, m is equal to the second point minus the first point. So let me color code. That's the second point. And let me draw this. First point. So we're going to say, okay, 3.996 minus 4. So that's the change in y, because, y and y. And negative 1.999 minus negative 2, so plus 2. When we do that, we get negative 0.04 over 0.001. We get negative 4 as the slope of this line. All right? So what we're saying is the slope of what is technically a secant over here, it's going through 2 points, that's approximately equal to the slope of the tangent. And in non-fancy words, slope of 2-point line is roughly equal to slope of 1-point line, just because the 2 points are very close to each other. And the slope in this case turns out to be negative 4. Yay, cool. That is, we just calculated our first derivative. That's a cool word, right? Derivative. I'm going to explain what it means too. So a derivative is the rate of change at 1 point. That's what we just calculated, That's what I kept saying. We want to find the rate of change of a line at just 1 point. We can't do that. That's not how the formula works. We need 2 points. Well, what if we just pretend that we have 2 points and they're just really, really close together, and then we can just use the rate of change formula anyways. And it will be like the rate of change of this 2-point line is roughly equal to the rate of change of the 1-point line. So that's the first definition of what a derivative is. Where is it? Over here, I found it. Rate of change of a 1-point line. Yeah? Now, a couple of things to keep in mind. Let's say that we just calculated, this derivative at this 1 point, negative 2, negative 4. That's not too useful. Come on, like, am I gonna go and like draw all these points and like lines every single time I want to calculate? What's the rate of change at this point? What's the rate of change at that point? That's gonna be pretty inconvenient. So for example, let's say I want to do it all over again. Okay, I have these 2 points over here that are pretty close together. Let me maybe clear some of this mess. Whatever. So now I have these 2 points right here, and I want to like do the whole thing again. Like I'm gonna draw it out, and I'm gonna like add a new line that is roughly equal. And now I'm like, okay, these 2 points, I'm gonna focus on them. And like the same thing over here. Like let's say I add another point, and I'm like, okay, fine. Like let's do it. Let's add this point over here. And now like I'm gonna draw a secant technically, but approximating a tangent. Non-technical words, 2-point line approximating a 1-point line. I'm gonna do it all over here. You can imagine this gets pretty tedious. Like you have infinitely many points on these lines. You can't do this all day. So we need like a better solution here. Am I right? Or no, you wanna just draw lines, that's fine too. Drawing lines is fun. What are we gonna do? We need a solution here. So here's what I'm gonna do actually. I'm gonna say something that's a bit weird. So when we calculated our derivative the first time, we got out this value, negative 4. Now, what I'm telling you here, can you look at like this line and this line? They seem pretty similar, right? Except it seems like this one's going down, this one's going up. If you actually calculated the slope of this green line versus the slope of this blue line, you would actually get that the slope of this green line is equal to 4. The slope of this blue line was -4. Remember, a negative slope means it's going down. The slope of this blue line is 4. That means it's going up. So what you're basically getting is like if you took the slope at every single point, you would get like, okay, slope is 4 here. So I'll put like a point over here at 4. Let's put a bigger point. That's a nice big point. And then if I took the slope that I got over here, -4, again, I'm just like doing dumb things here. I'm just plotting the points in a graph. Why am I doing that? So, I would put it somewhere down here. Eh. And then like I could draw a line through that, essentially. I could draw a line connecting these slopes, the slope values that I got. Eh. That is such a terrible drawing. Please forgive me. So I'm going to erase this mess, but the key idea is I can calculate a bunch of slopes for a bunch of lines and a bunch of tangent lines at that. So for a bunch of points, remember, this is what we call a derivative, the rate of change at one point. And once I get that rate of change at all of these different points, I can actually draw a line as if it were a new function. I could draw like, okay, this is y equals x squared. That's the regular function that we have. I could say, okay, we're gonna have a new line and let's just call it, what do we want to call this line? I'm gonna call it Bob for now. We're gonna give Bob a better name. We can say line Bob is equal to another function. Let's say 2x. I didn't pick 2x randomly, I'm cheating, but you don't know that for now. Pretend I'm very creative. We could make a line like that. And, we could make a line that connects together all of the rates of changes that we find at one point. So that's actually the way people like to do derivatives. They don't like to calculate, okay, this point, get another point close to it. They like to say, okay, if I have some function y or some function f of x, then I can calculate another function, which I'm going to call Bob for now, that gives me the derivative, the rate of change at any point x. So like, let's say here, I got put in x is equal to 2, I get out 4. That's the value that I'm getting out on this graph. Then for that derivative function, I would put in x is equal to 2, and I would get the rate of change at that point. So that would be the slope of the tangent line at that point. Am I making sense or confusing? Let me know. Thumbs up, thumbs down. Some people get it, some people don't. All right, let's try another visual. So here's what we have. We have this defined as a function, right? Let's see. So at the point where I'm talking about derivative is the rate of change at one point. Does that part make sense? Everyone's good there. So let's just erase all of the other mess for now. Does it make sense that if I wanted to calculate this derivative, which is just in the end a rate of change at one point, does it make sense what I'm saying that I have to find like 2 points that are very close together and like draw a new line through it? Cool. Let's just keep going there. So that's one definition of a derivative. You understand that? That's cool. So rate of change at one point. Keep in mind that y and f of x are the same thing. So y is equal to f of x. It's just two ways of saying the same thing. Remember, this is the output of a function. This is the input. So when we're measuring slope here, here's another way to look at what a derivative is. It's how much an output changes with a tiny change in the input. Why is that? Take a look again. Well, the output changing, the outputs on the vertical axis, that's like how much do we have a change in y? The input changing, the input is x, how much do we have a change in x? And that's what we did here. We said, okay, change x a tiny bit from -2 to -1.999. How much did y change? How much did y change? That's what we asked. That's what the slope formula is doing. It's calculating how much does y change based on a change in x. Except with derivatives, we're saying, hey, the change in x has to be really tiny. The change in input has to be really tiny. And we have to see then how much does the output change. It's a little bit like we have these set of knobs. So we have a function x, you put in the input, and you can like tune the knob. You can turn it left or right. And your job then is to see, okay, let's say I move the knob a little bit to the left. What happens to the change? What happens to the change in the output? So it could be that I move it, a little bit left, and the output also goes a little bit left. That's what a derivative is trying to measure. One way to look at it is rate of change at one point. That's what we saw here, rate of change at one point. The other way to look at it is we have an input and an output, and we see, okay, tiny change in input, how much does the output change? Or if this picture you like more, if we change the input knob, how much does the output knob change? Is this making sense? I want to make sure everyone understands this, because this is the key idea. This is the big thing you need to get away from this lesson. This definition of the derivative. The rate of change is like what you learn in math. It's nice. Whatever, it's cool. Okay, rate of change, 1 point. That's weird. Except this thing, this is like really powerful. Imagine you're a government. You have to decide, okay, we have to spend $1 billion. We can maybe decide to build highways or hospitals. We have to figure out, okay, how much, given the change in the inputs, how much money we spend, how much benefit do we receive? That is a derivative. Given each dollar we spend, so let's say we spend $1 more, that's a tiny change. How much more benefit does it do society? Let's say you're a pharmaceutical drug developer. You're like, okay, given each milligram of the drug that we give to the patient, how much more is their health improved? Given the change in the input, a tiny change in the input, how much does the output change? This is what is so powerful about derivatives. It's not just like some random graphing application, though that's how it's presented as at first in math. In the end, the only reason we have a graph is because we've just chosen to represent the information that way. That's what I said last lesson. We just put the information as input on this axis, output on this axis. And that's what we're doing with the slope. We're seeing input change versus output change. This derivative is just making that very small. So this is very key. This is the big idea to take away from this lesson. Derivative, how much does the output change with a tiny change in the input? All right. Can anyone else give me, I really need to make sure you're understanding this point. Can you give me an analogy of like what is another situation in life where you might measure a tiny change in the input and then figure out how much does the output change? So I showed you government, economic spending. I showed you healthcare. How much does the drug affect the patient? Any other relationships? Arjun?
Like the amount of gas you put into the car. I mean, like how much you press the accelerator, how fast you go forward.
Yeah, exactly. So let's say I press the accelerator 1 degree more down. How much faster does the car get? Does it get like 3 kilometers faster, 4 kilometers faster? Aris, do you have an idea?
Yeah, another example could be like adding salt to food. Like how does it taste after every little bit of salt you put?
Heck yeah. Ciara?
Another example could be how much could like based on like every minute more that you study, how does that affect how you do
Yeah.
on the test?
Yeah. So per minute of extra study, what percent does your grade go up? This is why derivatives are so powerful. This is why calculus is so powerful. You can take any situation in life and you're like, okay, what is the benefit of each extra thing I do? That is really powerful in so many disciplines. So I really just want to highlight this point. If you get nothing else away from this level, from this lesson, this is the big thing. So if you guys understand this, here's the big complicated-ish part. Now, when we're taking derivatives, we don't want to say like, X here is the amount of dollars we spend. F of X, the output, is like the benefit we do in an economy. We don't want to have to draw all these graphs. We don't want to have to like take all these little points. Well, surely there's got to be something better. So that's where we turn to the algebraic representation. That's where we say, okay, if we have some equation where we can, put in an x value and get the output of the function, we want another such equation that we can put in the x value and we get that rate of change at just that point. So we want another magic equation that gives us that rate of change. Do you guys understand what we're looking for? We want that other magic equation. How are we going to get it? Let's find out. So I don't know where it is. So what we actually call this equation, I called it Bob before. You can call it Bob if you want. That's fine. That's cute. We take a function of x. So we have an equation where we put in an input, we get out an output. We want another equation, which we call f. This is a comma, but it's read as prime. F prime of x, so that we can put in some value x and get the rate of change at that one point. Okay? Calculus is going to give us a rule to calculate that. But do you guys get this notation? Let me see the chats. All right, Julia, that's fine. So this is just notation, what I called Bob earlier. You can start a petition if you want. I don't know. Like maybe Bob is more entertaining than this notation. There's this other notation. So remember what we're trying to measure here, how much output changes given a tiny change in the input. That's shown as change in y over change in x. So what we're saying is, okay, we just want a very tiny change in the input, and that's going to create a tiny change in the output. Instead of calling it delta y over delta x, we have another similar notation, which is d of y by d of x. It's just saying the exact same thing. So change in y over change in x, but it's a really small change in y, and it's a really small change in x. So we just give it like fancy words. So our mission here is figure out how do we get from this function, or d of y by d of x, not d of y over d of x, d of y by d of x. It's used for this type of statement where you don't have like the f of x notation, you have y is equal to x squared. So that is what we're going to figure out now. This is where the rules of calculus come in. And I think this is where a little bit more of the memorization comes in. So I want to stop this lesson here and start recording again. But the key idea is we're trying to figure this out. How much does the output change with a tiny change in input for any input? We don't want to draw up the graph. We don't want to put in the points. Are you guys cool for now? You get the theoretical parts? Arjun, you don't look happy. You're like, screw calculus. I don't want to be here. That's all right. I understand. It's hard. All right. So I'm going to stop this recording here, and we're going to go to the rule in the next recording.